Hi guys. Okay, so we are continuing chapter 4 homework questions further. In this video, we are going to deal with the questions that relate to electronic configuration. And these are the problems 45, 47, 51, 53, 55, 57, 59, and 65. Okay, so just a brief overview or a review of what is the electronic configuration and the orbitals and those things. So for more details, you should look at the lecture videos, but here I'm just going to be a fast review. So we know that the atoms is made up of the nucleus, and atom is made up of the energy levels. The nucleus is the center. The main bulk of the atom is because of the nucleus. And inside the nucleus, there are protons and neutrons. But outside the nucleus are the energy levels. These energy levels are labeled as 1, 2, 3, 4. So energy level 1 contains one subshell, and one subshell contains only one orbital. Now, what is the meaning of that? Now, just like you see, when you are giving an address of a person, you're trying to locate a person, you have something to deliver. So what do you need? You need to know the name of the city. You need to know the name of the street. You need to know the house number, right? And in the house number is that person, and you deliver the package there, right? So same way it is, we are trying to locate the electrons, or we are trying to place the electrons. So where are the electrons found? Orbitals. The probability of finding the orbitals is maximum. The probability of finding the electrons is maximum in the orbitals. Okay. Now, orbitals are the houses. The subshells or the sublevels are the streets, and the energy level is that big city. So the bigger the city, the more the streets and the more the houses are. The smaller the city, the less number of houses there are and less number of people live. So that's a simple concept here. This is the energy level 1. So it contains one subshell, or it contains one sublevel, and that one sublevel is containing only one orbital, and the name of this orbital is 1s. Next, energy level 2. Energy level 2 is made up of two subshells. The names of the two subshells are 2s and 2p. Energy level 3 is made up of three subshells. Those three subshells are named as 3s, 3p, and 3d, and these are the orbitals. So every sublevel or subshell has the orbitals. So first energy level has one orbital. Second energy level has two orbitals, s and p. Third energy level has three orbitals, spd and spd. And the fourth energy level has four subshells and four orbitals, s, p, d, and f. So as many number of energy levels there are, then that many number of orbitals. Okay. Now, energy levels, obviously, the lower the number of orbitals and the subshells, that means less number of electrons are going to be found, but these electrons are closer to the nucleus. Energy level 1 is closer to the nucleus. Energy level 2 is a little bit further away from the nucleus. Energy level 3 is further away. Energy level 4 is farthest. So with that said, the more the space is in an energy level, the more the freedom is present. More freedom means more energy, more movement. So less energy, less space the electrons have to move, obviously less electrons can be accommodated. So with that said, the SP, D, and F, S being very small and has the lowest energy, F having the highest number of orbitals, these are also they also have the highest like the highest energy. Okay, so the energy increases from S, P, D, and F. Now here you see is the shape of the orbitals. Now S orbitals are really small, so they are all spherical in shape. The only difference is one S orbital is a little bit more compact. 2s orbital is a little bit more spread out, and 3s is very spread out. So in other words, basically these are the regions in space, the electron clouds, where the electrons can be found. Okay. Now, the shapes of the orbitals S are the spherical, but p orbitals have more dimensions, more length, width, and height. So you see X is horizontal, The vertical is, ideally it should be Y, and the Z should be like diagonal. But so these are the length, width, and height. So all the three dimensions, you are going to find the p orbitals, the electrons in the p orbitals. So p orbitals are 3. Right here, these green ones are the p orbitals. So you see the green ones are these 3. Okay, px, py, pz. And in each of the lobe, one electron is found. One electron is here, another electron here. One electron here, another here. One electron here, another here. So every orbital can hold a maximum of 2 electrons. But if you add all the 3, then you have 6 total. P can accommodate a maximum of 6 electrons. And if you look at D, D has got more lobes, more degree of freedom, more shells, more orbitals. So in other words, the D orbitals will be able to accommodate 10 electrons. So 2 are found in this way, 2 here, 2 here, 2 here, and 2 here. So these shapes are the shapes for d orbitals. Similarly, f orbitals have more lobes, more degree of freedom. Regardless where the electrons are, in which orbitals, they will always have the opposite spin. One moving clockwise, the other moving anti-clockwise. Okay. Now, here is this table which you're going to use in reference to answer some of the questions. Okay, let's see if we can make it a little bit bigger. Yeah, so right here. So you see here that the table, this table represents the electron capacity. So energy level 1 subshell, the name of the subshell is 1s, and the name of the orbital is also called 1s. Number of orbitals present in the s subshell is 1, and only 2 electrons can be accommodated there. Then comes the second energy level. Number of subshells are 2, and the type of sublevels are, or the type of orbitals are 2s and 2p. S can hold a maximum of 2 electrons. S is only one orbital, but p is the three lobes. You see that? Px, py, pz. So those 3. S is the spherical, one spherical. So S can hold a maximum of 2, but P can hold a maximum of 6. Now, third energy level, made up of 3 subshells. Name is 3sp, 3s, 3p, and 3d. Number of electrons in S is always going to be 2. It's always going to be one orbital. P will have 3 orbitals, that region in space, the clouds, and each of those is going to accommodate, the P accommodates 6 electrons. And then 3D can accommodate 5 orbitals. And so 5 orbitals, 2 electrons can live in each orbital in a opposite spin. And so that's how that d orbital, 10 electrons can be placed. Similarly, if you look at it, the same pattern, s orbitals 2, 3 orbitals, 6 electrons, 5 orbitals is 10 electrons, and 7 orbitals is 14 electrons. Okay, so a maximum of 32 electrons can be found in the 4th energy level, 18 in the 3rd energy level, 8 in the 2nd, and 2 in the 1st one. Okay, so now let's look at the orbital filling. Now here's the thing, since we know that these electrons are found in these energy levels, and then subshells, and then orbitals, they are present in the orbitals, and we see that P is present in 2p, 3p, 4p, 5p, and 6p, and so forth, 7p, right? And then D starts from the 3rd energy level. So we will see 3D, 4D, 5D, 6D. And then F starts at, after the 6th. So then F is like, is also in between. So it's not a linear way the electrons are placed in the energy level. There is an overlap, and the overlap occurs because it's in 3D, right? It's like a sphere. So yeah, the energy levels are going to overlap. Specifically, that energy level, which contains large number of electrons, in that case, it becomes, cumbersome. It overlaps. So look at the overlap now. So think about it. Now here where it says 4.7, think about it. Here is the I of the nucleus. So what is the nucleus doing? Nucleus is able to, now you have to imagine, nucleus is able to see 1s electrons more. Then nucleus is able to see, nucleus doesn't move. The electrons are the ones who are moving all the time. So nucleus can see the 2s orbitals, the electrons in the 2s orbitals more. So nuclear pull is more on the 2s orbitals. That is why they are in a lower energy state. After 2s comes 2p. Okay, so after 2p comes 3s. After 3s comes 3p. Now, after 3p, logically, it should be 3d, but 4s is a smaller orbital. Nucleus is able to see 4s more than 3d. Now, there is a concept of shielding effect. Shielding effect is when the nucleus is trying to look at all these single electrons, some of the ones that are in front, they kind of block the view or they shield the view. That is why it's shielding. So in other words, you see 2p is coming before 3p. 3p is coming before 4p. And so the nucleus will be able to little bit see 3p if the electron clouds, move. So that's why the effect, the nuclear pull begins to decrease and the overlap of these orbitals occur. So this is an overlap. After 3p, 4s is coming. Ideally, it should be 3d, but it's 4s. After 3d, we see 4p is coming. And after 4p is 5s. After 5s is 4d, 5p, 6s, and then 14f, 5d, 6, p, and so forth. Okay, so we see this is the very powerful one. Okay, now I have actually condensed it. This thing, and like many versions of it are also found in different books, but I've condensed it and I've tried to keep things simple. So here you see now is the a simpler view of the periodic table. Okay, now look at that. For s orbitals, very interesting how the periodic table got laid out. Okay, so here you have the s orbitals. S orbitals can hold a maximum of 2 electrons, right? So this is the reason why you will see 2 columns for group 1a and group 2a. The last electron, the valence electron, ends in like either one, like in the s orbital, but either it would be fully filled or half filled. If only 1 electron needs to be filled, group 1a. If 2 electrons need to be filled or are present in the valence shell, then group 2a. Okay, so valence shell 1 electron, if it is present in 1s, then it would be 1s1. If the last electron is in the second energy level, it's 2s2. If the last electron is in third energy level, it is 3s. It is 2s1. It is 3s1. Last electron is in the fourth energy level, it's 4s1. In this case, if the last electron is in the s, ends in s. Okay, so 4s. S1, this is 5s1, 6s1, 7s1. Okay, so that is the electronic configuration of the last electrons, the valence electrons for the ones belonging to group 1a. Now group 2a, all these are 2. So s2, 2s2, 3s2, 4s2, 5s2, 6s2, 7s2. Okay, next is now as many columns these are, as many electrons that can be accommodated. So P can hold a maximum of 6 electrons, like S can hold a maximum of 2 electrons. That is why 2 columns. P can hold a maximum of 6 electrons. So where do we see? 1, 2, 3, 4, 5, 6. See, so the last electron here is 2p1, 2p2, 2p3, 2p4, 2p5 and 2p6. Okay, same is the case here. 3p1, 3p2, 3p3, 3p4, 3p5, 3p6. Same story with the D. D can hold a maximum of 10 electrons. There are 5 orbitals, but a total of 10 electrons. So how do you make this? So this is 3d1, 3d2, 3d3, 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, and 3d10. Same as the case, you have this 4d and 5d and so forth. Okay, and then the F, interestingly, these are the 14 columns. So, all right, let's do the homework questions now. So we have this very basic understanding, and this is how they make the orbital diagram. So we will discuss that also. So let's look at the question number, which is 45 and 47. So I think I missed here 45 and 47. Sorry about that. Okay, 45. Indicate the number of each in the following, and 47. Okay, so let's look at that. Give me a minute. Okay, so question 4.45, part A, indicate the number of each of the following. So the number of orbitals in the 3D sublevel. So you look at this table and look at the 3D sublevel, type of sublevel 3D, and the question is asking how many orbitals are there. So you see, read this table, number of orbitals is 5. So that's the 5 number. So I'm just putting it on a separate sheet of paper here. Okay. Next is how many sublevels are in when n is equal to 1. So here is your n is equal to 1, and number of sublevels is 1. Next is orbitals in the 6s sublevel. So we don't have, now here's an interesting thing, we don't have in this table 5s and 6s. So we just only have gone till the 4th energy level. So they are looking at the 6th energy level. But look at the pattern, 1s, 2s, 3s, 4s. So s is present in all, and s has 1 orbital. In 4s, 3s, 1 orbital, 2s, 1 orbital, 1s, 1 orbital. So we see that the 1s, so this is every, so regardless, whenever there is s orbital or s subshell, it will always have s orbitals. Similarly, p subshell will have the p orbitals. So p, regardless if it is at 2, regardless if it is at 3, or if it is at 4, it doesn't matter. It will always have 3 orbitals. Okay. Same is the case with the d orbitals. D orbitals start from 3D, so they contain 5 orbitals. Okay. D subshells, 5 orbitals. All right. Next is the orbitals in n is equal to 3 energy level. Now they're looking at n is equal to 3 energy level, and they're asking how many orbitals are there. So total number of orbitals they're asking 5, 3, and 1. So this is 5, 3, 1. Okay. So that's how you just have to look at the table and answer it from there, looking at that. Okay. So that's one piece. Next is maximum number of electrons in 2p orbitals. Now, this is a so this seems like a typo error in your book. Okay, so 2p orbitals, maximum number of electrons in 2p orbitals is 6. Next is maximum number of electrons in 3p sublevel or 3p subshell. How many maximum number of electrons are there in the 3p? So remember, 3p, all this is still a part of it. So this is 5, 3, and 1. So that's like number 9. Okay, so that's number 9. Next is when the energy level is 4, how many electrons are there? So total electrons, 32. Okay, and then 5D sublevel. So in 5D, so once again, how many electrons are there? D can hold a maximum of 10. S can hold a maximum of 2, and P can hold a maximum of 6. So then that means 5D orbitals. 5D orbitals will contain, the maximum number of electrons. 5D sublevel, 5D sublevel, maximum in the D is always going to be 10. Okay, so keep that in mind, that the shell number and the orbital number, the name is the same, but S is present in each of the energy level. 2s is also present, 3s is there, 4s and 5s and so forth. P's are also present in each, D are also present in, like, each, but it depends where they start. So 2 So 2p starts at the second and 3d starts at the third and 4f is at 4 is at f. Okay, now here you will see next is the electronic configuration. Okay, so based on that we already talked about the periodic table. Now interestingly, the electronic configuration is based on this. So what does this mean? This means that the energy level so it would be 2 electrons can come here, so that becomes 1s2. When next, if you're placing the electrons, now you just have to imagine that you have a cage, and in this cage you have to place the atoms and electrons. So you have these different, marbles, which represents the electron, and then you have these balls of different sizes, each representing the atom. So let's say you fill the cage with all the balls. That means the nucleus of every atom is already placed. Now we need to place the electrons in the outermost shell. So what order are we going to follow? 2 electrons are going to go in 1s2. If we have more, then 2s2. If we have more, then 2p6, then 3s2, then 3p6, then 4s2, then 3d10, then 4p6, then 5s2, then 4d10, 5p6, 6s2, 4f14, 5d10, and so forth. You get that? Okay, so it is like visually this is showing like this, but I have actually, let me stop sharing this now. So before we go, I want to just highlight that now our questions are from here. So we are looking at these questions. Okay, so we will look at 51, 53, 55, 57, 59, and then 65. Okay, so hang in there. Okay, so now I have written this. This is a linear form, like a placement. More like, I think it's students like to see it more things in a linear fashion. So the filling of the electrons follows this order: 1s2, 2s2, 2p6, 3s2, 3p6, then comes 4s2, then comes 3d10, then 4p6. After 4p6 is 5s2, then 3d10, then 5p6, then 6s2, 4f14, 5d14, 6p6, and 7s2, and so forth. Okay, so let's do first the orbital diagrams. Now let's look at for boron. So boron is B5. So you're only going to look at the atomic numbers now. Okay, so 1s2. So we need to place 5 electrons. So 1s2, then 2s2, because 2 can hold a maximum of 2 electrons, and the remaining electron goes to 2p, and we need to only place 1 electron. Okay, so when you count these numbers, 2 plus 2 plus 1, they match to 5. Besides that, now, interestingly, look at the placement of boron. Okay, where is boron placed? Boron is placed in group 3A, right? Boron is in group 3A. That's one piece. Second thing is boron is present on the P block. Okay, and boron is present in the first column. So one question that student asked me is that placement is fine, but where do you stop? So this is where you stop. You see the placement of boron, it is in the first column. That means it's going to be P1, and it is in the second energy level, 2. Okay, so second energy level, so it should be 2p1. Okay, so let's look at this now. So the placement, although this is placement, is 2p1. So what does this mean? This means this one means the first column in P block, first column, and then this is the P block, and 2 stands for the second energy level. Okay, so that's what you see here. First column, the exact same things you see here. Okay, so now we have to, when they ask, so generally for the orbital diagrams, we look at the last, the valence shell. So these are the valence shell, and valence shell means the last shell, the last energy level. So last shell is the last energy level, and that last energy level is the second, second period or second energy level. Or let me just put it this way, that n is equal to 2. So second means, this is the second period, means n is equal to 2. Okay, so P1, as we talked about, the P block, first column. Okay, now when we talk about the valence, now valence shell electron, so you can just do it like boxes or circles, it doesn't matter. So, but this is 2s and this is 2p. So the rule is that, first, singly occupy, but then in this case, this is one orbital, 2s2, and then 2p1. Okay, so these are the 3 valence electrons basically. Okay, so this is what it means. And you can like create the inner core is that of helium. Helium is what? Helium is 2. Okay, so helium is 2. Let me just do this here. Sorry, this is helium 2, and then 2, 3, 4, 5. Okay, so that's how you write down for boron. Now let's look at aluminum. Now aluminum is 13. Aluminum is 13. So we will do here 1s2, 2s2, 2p6, 3s2, 3p1. All right, so that's what we have. Next piece is the inner core. The inner core looks like the nearest noble gas. So that nearest noble gas in this case is neon 10. And in the valence, we have 3s2 and 3p1. And the orbital diagrams look like this: 3s2 and 3p1, 3s and 3p. And so here you have, let's just do it in red. So here is the 3s2 and 3p1. And here the inner core is neon. Okay, and that is the electronic configuration for aluminum. All right, so that's, and the rest of it you should do yourself, but you can draw the orbital diagrams like this. Write the electronic configuration of boron. So that is the problem number 4.53. So boron is 5, and this is 1s2, 2s2, and 2p1. So, that's these numbers on the top add up to 5. Sodium is Na, and sodium is 11. So 1s2, 2s2, 2p6, and 3s1. Now, if you look at also the placement of boron is 2p1, the placement of sodium is 3s1. Okay, so that's the third energy level, S block and first column. Let me write this down. Third energy level, S block and first column in S block. All right, now here you have the 3s1. Okay, so the inner core looks like the neon, the noble gas, and neon has 10. So 6 plus 2 plus 2 is 10. So 6 plus 2 plus 2 is 10. Okay, and then this becomes 3s1. This is 3s1, 3s1. Okay, and that is the sodium, Na. Okay. All right, next is the abbreviated electron configuration of silicon. So how do you know? Because generally, with time, we remember, but silicon is 14, okay? That 14 is the atomic number or the number of electrons. All right, let's look at silicon now. Now, another thing I want to show you is that, look at that. Silicon, it's always the noble gas, which is one period above. So silicon is in the third period, Si, and neon is in the second period, one period above. So, all these electrons that are before neon, including the one that makes the neon, all of them, they are called an inner core for the third row elements. And then the same is the case with the fourth. Okay, so let's look at this. Silicon 14. Okay, silicon Si, and that's 14. So we need to write the abbreviated. So first, always, I like to write it like this: 1s2, 2s2, 2p6, 3s2, 3p 2. Okay, so look at this 3p2. 3p2 is, you have silicon here. Okay, silicon is present in the third energy level. Okay, third energy level. So if you look at this, sodium, magnesium, and then come all the way here, silicon. Now, interestingly, silicon is present in the second column in P block. That is why P2. Okay, third energy level is 3p, and then it's in the second column. Okay, so now let's look at the so in this case, this piece is like neon. 10 electrons is that of neon. Okay, and you have 3s2 and 3p2. So that's the the basic and then this is the valence electrons. Okay, the last shell. Now look at phosphorus. Now phosphorus is P. Okay, now P is present in the third column, so it will be P3, and it is in the third energy level. First energy level, helium, then neon is a second, and the third is argon. So third energy level is the phosphorus, and then phosphorus is in the third period. I mean, at the third energy level, third period, but it's also in the third column, and it is in the P block. Okay, so that's the deal with phosphorus, and it is phosphorus 15. Okay, so 1s2, 2s2, 2p6, 3s2, and 3p3. It is present in the third column. So let's write this here. This is the third column in P block. Okay, and third row, or that also means the energy levels. So here also you can see that this is the inner core, neon. So you have to match some, some of the elements, will inner core, you have to like count and see which ones represent the nearest noble gas, and generally the noble gas is one period above. Okay, so then this is 3s2 and 3p3. Okay, now symbols of the elements, which ones? Now you have to locate which ones are these. So the best way to do is here, if you count 6 plus 2, 8, 6 plus 2 plus 2, 4. So 14. So this is what, 6. So 2 plus 2, 4. So let me write this down here. So this is 2 electrons plus 2 electrons plus 6 plus 2 plus 6. Okay, so 10 plus 8. So this is all 18 electrons, and 18 electrons. Now you go back to the periodic table, look at 18 electrons. So you see 15, 16, 17, and 18. And 18 is argon. Okay, so do this. 18 is argon. So this is argon, 18. All right, now which one is the next one? Now neon. So let's say you don't know what neon is or how to, so look here. This is the neon right here. So neon has 10 electrons. Okay, and so we're going to go back and see. So this is 10 electrons are here, and then 2 plus 1, 3s2 3p1. So this is one thing. This is 13 electrons. And then the next thing is, this also gives us a rough idea, or this is the first column, P block, and that is the third energy level, or third row, or third period, okay, energy level. All right, so 3p1. So look here. So obviously, this is the first energy level, second energy level, third energy level, sodium, magnesium, and then come here, aluminum, 3p1. So this is in the first column. Aluminum is in the first column in the P block, and it's in the third row. So it's aluminum. And anyways, it's adding up to 13. So it's aluminum. Okay. So aluminum 13. So this is one piece. Now let's look at this type of questions where they're asking you, what is the symbol? So what is the symbol of that element that has 3 electrons in energy level 3? So in other words, energy level, when energy level n is equal to 3 means the third period. Now remember that 3s, third period, third energy level is made up of 3s, 3p, and 3d. Okay, and they're saying 3 when n is equal to 3, and there are 3 electrons there. So where are those electrons present? It has to be in 3s and 3p. So 2 electrons can be accommodated here, and then since we only need to have one more, so one of them is here. Okay, so now third period, and it's the 3s2, basically 3p1. So you are looking at the 3 electrons. And n is equal to 3. Yeah, 3 electrons when n is equal to 3 in 3 energy level. Okay, so which element is that? So we just now looked at it. It looks like aluminums, because aluminum is in the third period, right? And that's the third period, number 3. And that belongs to, like, aluminum belongs to that period. And so it's 3s2 and 3p1. Okay, so that's aluminum 13. Okay, next is, which symbol of that element that has 2p electrons? So 2p electrons are present in boron. 2p, 1 is to 2 is to, yeah, it can be boron, it can be carbon, it can be nitrogen, oxygen, fluorine, and neon. So we don't know how many they are saying. They're saying that there are some electrons present in the, like, in the 2p orbitals. So it could be boron, carbon, nitrogen, oxygen, fluorine. So could be boron, carbon, nitrogen, oxygen, and fluorine. Okay, so that's the 2p. Okay, next is completes the 3p sublevel. So which orbital completes, like 3p is completely filled. Completes 3p means sublevels, subshells means like completely filled. And when we say completely filled, that means we are looking at p6. So 3p6 basically, we are looking at 3p6. So which element has that? Fully filled. So 3p is the third energy level, and p block, and it's fully filled. So it has to be argon 18, the last one, p6. Remember that first column the ending is going to be p1, second column p2, third column p3, fourth column p4, fifth column p5, and sixth column is p6. Okay, so it's argon. And then completes with 2s sublevels. So when 2s completely filled, which one? So 2s means the second energy level, and S is obviously the S block. Where did it go? Here. So 2s completely filled. So it has to be beryllium, because the first one is 2s1, the second one is 2s2, the third one is 3s1, and then it is 3s2. Fourth one is 4s1, and then the next is the calcium is 4s2. So all the ones that are in the second energy level will have the filled up s orbitals. So we are looking at the second energy level, so that is beryllium. Okay, beryllium 4. Okay, now next is the last question here, that use the periodic table to give the number of electrons in the indicated subshell. Now 3d in zinc, 3d orbitals in zinc. Use the periodic table. So look at the periodic table and look at zinc. Okay, zinc. Now they're saying, fine, zinc is in 3D, but zinc is in the last column, the 10th column. That means it will be completely filled. It will be D10. So in other words, scandium is D1, titanium is D2, vanadium is D3, chromium is D4, manganese is D5, iron is D6, cobalt is D7, nickel D8, copper D9, and zinc is D10, and it's the third energy level, 3D10. Okay, so go by the placement on periodic table. Okay, next is the 2p in sodium. So 2p in sodium is what? So here is the sodium. So 1s2, 2s2, and then sodium is 11. So 1s2, 2s2. So 2s2, and then comes the 2p6, and then comes the 3s1. Okay, so sodium is 3s1. So the rest, the top ones are all filled up. Okay, so here you have boron, carbon, nitrogen, oxygen. Oh, sorry. Which one are we talking about? I forgot. Sodium, 2p. So 2p is 2p6. It's all filled. So 2p6. Okay, so you can do the electronic configuration also on the side, and from there you can get it. So pretty much the rest of it you're going to do on your own. The other questions, that's a good practice. And we'll get back to the remaining questions, which is the questions 69, 67, 69, 71, 73, 75, 77, and 79, which relate to the trends in the periodic table. We will do it in the next video. All right. Thank you. Bye-bye.